I am the responsible of the solar thermal division of the ENEA. ENEA is started to work in 1960 on the nuclear program, Italian program. After around 18, I started to change the program. The research is oriented for the science of the life, because the nuclear Italian program is stopped, so it changes also the mission of the ENEA. ENEA is the second public research of Italy, and is straight at the facility and the possibility to work together with the industrial system, Italian industrial system. His mission is support the industrial Italian system and the public administration at the local and central level. The ENEA is divided in the 4 big departments. The first department is vetted to nuclear. Okay. The first department is focused on activity on the nuclear, normal nuclear, and the fusion. The second is activity. The second department is oriented to develop the renewable energy source. Under this umbrella, there is my division that is focused to develop the CSP technologies, together with the possibility to couple this technology with the smart grid. The third department is the science life, so environmental technology, climate change modeling, etc. And the fourth department is not really a department, is a new agency because it's the agency for the FTS and support the Italian system for this particular topic. The facility of the ENEA is distributed along all the Italy. The facility for the division is divided in 3 laboratories. The first laboratory is oriented to develop the technology for the solar thermal application. The responsible is Michele Lanchi. After, there is a second laboratory is to develop the technology engineering laboratory to support the Italian system to build the CSP system with the molten salt technology or without the molten salt technology. And the third laboratory is the smart grid that is oriented to develop, to study how to couple the thermal storage system, the CSP technology, and in general the different renewable sources in the smart power grid at the local level. The facility of the division is more or less concentrated in the main 3 centers. One is Cassaccia, where now we're here. The second is Portici, near to the Naples. In the Portici develop a special decoating and the smart grid application. And the third facility is concentrated in another research center in South Italy, Risaia, near to the Puglia. And about the facility present in the Cassaccia, here is already listed all the facility. For the reason the time I don't list all the facility, but tomorrow will during the visit you can to ask the information about the different facility. The topics of the study of the division is divided in the 5 lines. One is oriented to develop components and material for CSP application. The other line is to develop the thermal storage system coupled with the power grid system. The third line to develop technologies and systems for produce solar fuels with the solar system. The third line is to develop the smart technology for to couple the renewable sources with the power grid at the local level. And the last line is oriented to develop the qualification to support the industrial system. This means to share the qualification service, for example, to test the different components, material, etc. That's all. Thank you for to be present today here, and now we start the real course. Please, Michael.
Okay, so good afternoon again, everyone. It is a pleasure, a great pleasure for us to host the first FASTRA school organized within the SALTOpower project by ENEA, DLR, and University of Évora. And the aim of this project, of this school, is to deliver know-how on concentrated solar power and concentrated solar thermal technologies, which use molten salts as heat transfer fluid and heat storage material, and also to train candidate and young researcher industry on the research topics, on research methodologies, and on the results gained within the SALTOpower project. And now, very quickly, let's come to the protagonist of this course, which is the use of molten salt as heat transfer fluid and heat storage material. Why are we so interested in it? ENEA has started to develop, for example, in particular, the concept of linear CSP technology using molten salt as heat transfer fluid and heat storage material since the early 2000s, replacing the more conventional linear CSP concept, the plant using oil as heat transfer fluid and molten salt and as heat storage material, and obviously gaining these advantages. Higher operating temperature in the solar field, which leads to a higher temperature difference in the power cycle, consequently a higher thermal efficiency. The reduction of another advantage is the reduction of the size of the thermal storage, again for this temperature difference, this big temperature difference, and the removal of the heat exchanger between which connect the heat transfer loop, heat transfer fluid loop, and its storage unit, and finally also the lower environmental impact of the molten salt compared to the diathermic oil. And again, referring to ENEA, the development of the DNS technology from the design of the components to the realization of the first Italian commercial plants has required something like 15 years, passing through the laboratories testing of components and materials, through also the realization of a facility, a real-scale facility for characterization of real-scale components in real environment, through also the realization of demonstrative plant, like the Archimedes plant and the METS plant, which was realized in 2018 within a European project coordinated by ENEA. This is a cogenerative plant which produces electricity and desalinated water. And currently, not working. Okay. Currently, the ultimate research objective on this field is to enhance the energy performance, reduce the cost of this technology. And the research activity that has been carried out by DLR, ENEA, and University of Évora on this field is supported by the use of unique experimental infrastructures, unique in Europe, which can be used and applied for the real testing of real components in real environment, but also for the testing of procedures and operational procedures. And here you can see the PCS plant located in the ENEA Cassaccia site, which will be visited tomorrow by the on-site attendants, and the HPS2 molten salt loop of Évora, which is a full-scale molten salt pilot CSP plant, and this facility of DLR located in Cologne. And now let's start, after this very quick introduction, let's start with the course. This first edition of the FASTRA school includes molten salt focused lecturers dealing with basic research topics and state of the art, and also a research brainstorming. And particularly today we will have a very quick overview on the use of molten salt in CSP plants and also for the application of provision of heat to the industrial processes. And along with some technical aspects related to the thermophysical properties of molten salts and chemical stability, thermal stability, and also material compatibility. While on the second day, we will have the multi-application of molten salts in thermochemistry, Carnot batteries, thermal storage will be evidenced, together with a discussion on practical aspects related to the operation and commissioning of molten salt plants. And on the afternoon, only for on-site attendance, tomorrow we will have a technical visit to the ENEA research infrastructure, followed by a research and brainstorming. And now let's start with the school. Before going on, I would like to underline that you will have the opportunity to ask questions to the lecturers, but preferably the questions should be written on the chat and then discussed after the conclusion of each presentation. And now let's start with the first presentation given by Jana Stangler, who is a chemical process engineer by education. And she has earned a PhD in energy and process engineering from the University of Stuttgart. She works now at DLR. She has a background in thermal energy storage, thermochemical heat pumps, and waste heat recovery from industrial processes. And she joined the DLR Institute of Solar Research in 2020 as group lead of the Fluid Systems Research Group. And she is the DLR representative in the steering committee of the Evora Molten Salt platform. So, Jana, please.
Okay, so welcome to everybody also from my side. I'm very happy that I can give you the first overview of this fast track school. And we have a pretty broad audience. So there's a couple of engineers here in the room, scientists, and I saw that online there's also about 50 people. So I guess there's like all the range from PhD students who just joined the topic of CSP, but there's also engineers who've been working with CSP and molten salt for a couple of years. So I got the challenge that I need to cover everything. So we have a common start. So if you're already experienced engineer or scientist in this topic, there are not going to be too many new issues here or new topics for you. It's just meant as a common start. But that also means that I'm the lucky one who gets to show you all this really impressive photos of CSP plants at utility scale. For example, to start with that NOR plant, I think it's a very impressive view. At least I really like this or enjoy those images. You see here there's different technologies. It's one plant, but you see there's a tower, but there's also troughs. So this is a good image for the overview of this presentation today. So what we're going to cover is examples of commercial plants as a start. We have a look at different technologies for CSP very briefly. Then we have a look onto molten salt or the standard solar salt that's been used as heat transfer fluid, but also as heat storage medium. And then we'll have a look in current research topics to give you an idea about the structure of this fast track school. So you have guidance for the next topics or talks. So another example that I picked is Andershall. It's the first public trough project that we had in Europe. At least the first commercial one. It was commissioned in 2009, so it's a pretty impressive plant in the south of Spain. Maybe some of you already had a chance to see it. It's parabolic trough. Then was another example that I picked, Gema Solar, also in the south of Spain, with 20 megawatts. It was the first utility scale or commercial scale tower system in Europe. And only a couple of years later, this one was commissioned in 2011, and in 2015. In the United States, we had the project of Crescent Dunes, with also a tower with molten salt. So it's a bigger project with 110 megawatts. So you get a pretty nice impression about the different technologies and how they developed. There's also a couple of examples from China. I just picked one. It's the biggest linear Fresnel project that we have in the world. I think it was only the first Fresnel project in China. It went on in December 2019. It has 15 megawatts thermal rating and 15 hours storage. It's a linear Fresnel with molten salt also as heat transfer fluid. So this gives you an impression about the different technologies that we're using. For example, there's solar towers, there's parabolic trough, and there's linear Fresnel. So it's point focusing technologies, but also line focusing technologies. And for line focus, I chose parabolic trough in linear Fresnel. Linear Fresnel basically has several facets, so they have smaller curved mirrors, but they also aiming the solar irradiation on one line focus. And so the molten salt that we use here has basically two functions. You can use it as heat storage medium, that's where it came from. Also that all power plants or CSP plants already features molten salt as heat storage medium. And the more like newer use case for molten salt is to use it as heat transfer medium in point focus and line focus systems. So let's have a look into molten salt tower technology. How does it actually work? So the standard would be to have a 2-tank system. So you use cold salt and circulate it through the solar receiver, heat it up, and then you can directly use it to produce steam, or you can store it in a tank and use it later. So you have one component that connects the molten salt loop to a conventional power block. And the rest is basically a turbine, steam generator, and so on, as you know from conventional power plants. So you have that conventional power block and two use cases of molten salt. And basically there's a lot of experience on large-scale thermal energy storage with molten salt. It's state-of-the-art. And for using molten salt as heat transfer fluid, there was some experience in France in tower systems, but also in the United States later in the 90s. So having heard that history and also having heard Michaela's introduction about the history of ENEA and working with molten salt, you could definitely ask yourself the question, so why are you still talking about molten salt here in a research topic? And I guess this is the questions that we will answer during that fast track course, to get to show you what's the developments, what's the open research questions, and also on utility scale. Coming back to that first photo that I had, that first Morocco, that NOR facility. What they have here installed is a solar tower plant with molten salt as heat transfer fluid. They have storage tanks also with molten salt. And although there was a project that went online in 2016 and 2018, so it's still state of the art, but still they would use oil as heat transfer fluid in parabolic trough. So let's have a look into the scheme. We briefly had this before in your presentation, but let's put it down. So what you would do in utility scale state-of-the-art parabolic trough CSP plant is the following. You would have one circle in the solar loop with thermal oil, and then you would use a heat exchanger to have another loop with molten salt to store the thermal energy, so to produce energy during night. And then there's another loop with thermal oil, so you could generate steam. So why would you use thermal oil as heat transfer fluid and not molten salt? So that's closely related to the physical properties. This is so very few numbers here, but still it's a kind of texty slide. But I wanted to point out that there's some physical reasons why you wouldn't use organic heat transfer fluid. If you see the working temperature, the good thing is for organic heat transfer fluids, there's some, for example, helisol, you could use below freezing point or below 0 degrees C. But it's limited to temperatures up to 400, maybe 425 degrees C. The heat capacity doesn't look too bad, actually. But if you're considering the low density, it results in a rather low volumetric heat capacity. So that's the reason why you wouldn't use it as storage material, but use molten salt instead, because in the end, this turns out to have a higher volumetric heat capacity compared to organic heat transfer fluids. And the standard solar salt, or the standard salt mixture that's used in CSP plants is solar salt. It's a mixture of sodium nitrate and potassium nitrate. There's other mixtures, and we will cover this later in this fast track school. It has about 240 degrees C melting temperature. So you need to make sure that every single component of your plant is equipped with trace heating, so you stay safely higher than 250, 260, 270 degrees C. That limits your lower operating temperature. There's several other benefits of using molten salt. It's not inflammable, it's not toxic. Also, the supply costs per kilogram are lower than with silicon oils or other thermal oils. And also, you don't see as much thermal degradation of the physical properties. As you see here on that slide on the left-hand side, it's a photo that was taken from different samples of organic or silicon heat transfer fluids. They've been kept for 10 days at a higher temperature compared to, it's 465 degrees C. And you see what happens. It used to be clear substances, and now the one is black or brownish and the other is yellowish. So it's a clear indication physical properties will change. And that's the reason why you go on molten salts instead for high temperatures. So let's assume you replace the thermal oil in the solar loop by molten salt. That has several benefits. First, you can increase the temperature in the solar field itself, but also in the storage tank. You don't have to add additional heat exchangers. I'll quickly jump back. So you can go directly from one loop from the solar field to the steam generator, to that heat exchanger. So in the end, with this few components and higher operation temperatures, you can increase the efficiency of the power block. In the end, that's up to a cost decrease. And these numbers are a bit older, but we've done the math, and we expect that you could get a 20% cost decrease from this high efficiency in the overall power block, and also from having fewer components such as heat exchangers. But of course, it doesn't come for free, those benefits. You have to cope with a couple of technical challenges. There's the danger of freezing, and it's hundreds of meters of parabolic troughs, as you just seen in the photo. So there's a lot of trace heating required. You also have to add trace heating for your receiver, or you have some means for solar preheating. That's the alternative. There's a couple of procedures that you have to really have an eye on, for example, filling and draining. So you don't want to have any cool spots in your receivers and all that hundreds of meters of pipeworks. And of course, there's so many surfaces and at high temperatures, there's increased corrosion rates. So this is something else that you want to keep in mind. And some of those challenges are tackled at ENEA and also at DLR and at the University of Évora. Just as a first start. So basically, that's a teaser for you to sign up for the next fast track schools as well. One of them will be held in Évora, where colleagues have that research facility for different topics around molten salt, for example, using molten salt as heat transfer fluid in those parabolic troughs. I will not go into this in detail. It's just a cliffhanger for the next fast track school. And if I remember, I had this one photo from China, just as another example for using molten salt in linear focus power plants. They have a Fresnel collector. It went online in 2019, so they should have 4 years of operation experience by now. I haven't heard any news about their experience, how they would handle filling or draining. So if there's anyone here who could share information on this, it would be really nice to have a talk to share info. And also, this is a good example why we need such facilities like ENEA, like the one that University of Évora has, because we need to offer some space or some infrastructure for doing experiments also on large scale for different industrial partners to test their components, for researchers to test their new procedures, their new salts. That's the exact reason why we have this school here, why we're still talking about molten salt research topics. Because there is some industrial projects, but still it's hard for us to have an insight on this. So, my last slide, some ideas, some approaches about new research topics. And it's not a complete overview. There will be missing very many topics. I try to break it down into like 4 different fields. Of course, they sometimes overlap, so it's not a clear structure, but it also kind of reflects in the agenda that we have of the rest of the fast track school. So if you're looking into material research, there's a lot of research being done on extending the working temperature range of molten salts. There's several approaches, for example, using other salt mixtures for higher temperatures or for lower temperatures, but also by controlling the gas atmosphere over that molten salt. So you can control your degradation processes. There's a lot of research also being done on the quantitative assessment of corrosion rates for different working materials or steels or alloys, but also we have a look on coatings. You need optical coatings, for example, in tower systems, but also you need corrosive resistive coatings for your pipeworks. If you have a look on CSP components, there's a lot of development being done on collectors and receivers. I guess we'll see some of them tomorrow when we visit the facility. Also for tower systems, that's a topic that we won't go into detail in this fast track school, but there's some ideas how one could optimize the efficiency of those receivers by having advanced structures or concepts such as a star-shaped receiver instead of the external receiver that's been used until today. Then there is a lot of operational experience that we still need to gather, for example, how to cope with freezing events. Sometimes we do this on purpose, sometimes that just happens and we have to cope with it. So there's a lot of developments also being done on trace heating on these aspects. And then we will also have another block tomorrow on thermal energy storage. From the commercial projects, there is some lessons learned that, for example, one weak spot of those tanks is the hot floor. So there's some studies going on how to improve this, welding techniques, for example. And then there's also an approach to reduce the number of tanks. So you could use one tank instead of two tanks by using a thermocline. So this will also be covered in our presentation tomorrow. And then if we further zoom out on system level, of course, there's a lot of activities now for process control, plant simulation, modeling, digital twin. So there's a lot of going on in this context. But also we have some activities on hybrid PV, CSP plants that will be talked tomorrow. Also different power to heat concept, kind of battery. So it really goes beyond the scope of CSP. And also the use of molten salt for process heat supply and in chemical reactors. So with this, I'd like to conclude. This is again a photo that I took only 4 weeks ago when I had the chance to travel to Ibra. Again, that's a teaser for you to sign up for the next fast track schools. I'm pretty excited to see your facilities tomorrow here in ENEA. So thank you very much for inviting us.
You're welcome.
Yeah.
You're welcome. Let's hope that we will not be forced to visit the facility under the rain, but
yeah. Let's keep our fingers crossed that the weather will be as here on that photo. Yeah. So with this, I'm thanking you for all your interest and attention, and I hand over to the next speaker, I guess.
Yeah. Thank you very much.
Thanks.
Okay. Thank you very much, Jana, for your very interesting presentation. And now let's leave the floor to Pedro Horta, Professor Pedro Horta, who is the head of Renewable Energy Chair, University of Évora, and responsible for the National Research Infrastructure on concentrating solar energy. He is also the coordinator of the SALTOpower project, which is under the umbrella of which we are holding this faster school.
Okay, thank you so much, Michela, for the presentation, and thank you so much, Marco, for the preparation. Well, good afternoon to you all in here and at home. I'm really happy to be able to talk to you a bit about molten salts. In this case, in the scope of process heat applications. So we have just seen an overview of what is molten salts and what has been its use for energy applications. Jana gave us a very good overview of its applications on CSP plants for thermal power generation. And I'm now going to talk very briefly about a possible application of molten salts in industry for industrial applications. So this is not yet the state of the art, but this is definitely a potential we can already recognize for the use of molten salts. Oops. Okay, perfect. Okay, so we are going to see how could it look, a system of process heat with the use of molten salts. We are going to talk briefly about molten salt mixtures and properties. How could we meet the requirements of process heat applications considering the use of these mixtures? And then finally, to just raise some questions on challenges and opportunities. I will try to deliver all of these contents in 10 to 12 minutes so that you still have some space for some questions, okay? Okay, what is process heat? Well, I guess this is broadly known by all of you and by all of the attendants, but basically we are talking about the use of energy for warming industrial spaces, of course, but especially for use in industrial processes. Okay, this is actually the core of process heat applications, the use of heat in industrial processes. And if we look into what does that mean in terms of final energy consumption worldwide, well, we can have a good estimate. Taking International Energy Agency numbers of 2019, so the industrial sector accounted for about 29%, okay, 30% of total global final energy use. So this is total, includes everything, transportation sector as well. And roughly 2/3 of that, it's used in the form of heat. Okay, so we are talking about 20% of the overall worldwide energy consumption. This is process heat. So it's definitely a very significant share of our energy consumptions. And one thing which is clear today is that, of course, process heat can be a number of different things. And we can classify process heat in terms of its temperature level. And we have applications at low temperature, so whatever processes occur below 100 degrees, there are a number of them. Then we have medium temperature, so processes occurring between 100 and 400 degrees. I must refer here that 100 or 150, 400 or 450. So there are some discussions in this field, but roughly 100 to 400 degrees. This is the range we name when we talk about medium temperature applications, and then above 400 to 450 degrees, above that we have high temperature applications. So if you look into the share of energy used in processes according to these different categories of temperature, we see that low and medium temperature account for roughly half of these consumptions. The other half are accounted for high temperature processes. So roughly 10% of the total worldwide energy consumption, it's in industry in low and medium temperature. 10% of the total worldwide final energy consumption, it's in industry in high temperature processes. So something we should take a look at. Well, we have already seen that molten salts are an interesting heat storage or even heat transfer fluids. It has good thermal stability, low vapor pressure. How could we use, or how could we heat these molten salts? Well, of course, with solar thermal collectors, and we have seen here a number of examples of such collectors, and definitely very impressive applications on thermal power generation through CSP. But we could also use green electricity with resistive heating to heat molten salts. So we have definitely the possibility to incorporate different renewable energy sources. So directly solar energy through thermal conversion at medium or high temperature, as we have seen, but also, why not, solar energy through photovoltaics or wind power or wave energy or other forms of green electricity generation. And then using resistive heating to heat the molten salts. So roughly, if we take the most common solar process heat application and integration, so those who are accustomed to process heat topics, they have already spotted that we are talking about integrating solar energy at supply level. What does that mean? That we are going to integrate this alternative renewable energy source close to the energy supply system already in place. Normally, this is a boiler. Okay, so a boiler generating steam by burning some fuel, biomass or fuel oil or whatever, natural gas most of the times. So we might have then a system which in parallel is able to also produce steam in parallel with the boiler. So we are integrating this new energy source at supply level. So we are not going directly to one process. Okay, industrial users are not very keen on touching their processes. That's something, to those of you who are not very knowledgeable about process heats, that's something I can tell you already. They don't want to touch their processes, okay? If you do something around the boiler, well, they can overlook, but not in the process. So this is the most traditional way of integrating solar heat into a process heat plant. So what we see here is that, well, we have the ability to have a storage system, and solar energy works very well when we have storage. So this is definitely a very important asset when you want to meet load profiles with solar energy availability profiles. And we can use molten salts as a storage medium. So not only we would have the ability to have a solar thermal field with solar concentrators, as we have seen already in the pictures before, but we would then also have the possibility to incorporate green electricity stemming from other resources in the grid. And so using these hot molten salts, we could then have an heat exchanger, molten salt, water to produce steam, and then integrating the steam in the steam distribution network of an existing facility. Okay, so this could be one way. There are others, okay, but this is, I would say, the most typical way of introducing molten salts as a means to store energy and to integrate renewable energy in a process heat system. So as my colleague Jana Stengler already mentioned, why molten salts? Well, they have some interesting properties. So they have high heat capacity, so basically the double of what we can see in thermal oils. Excellent thermal stability, so very resistant to degradation over cycles, so much better than thermal oil as well. High thermal conductivity, and this is very important whenever we consider the use of such a heat transfer fluid with heat exchangers. This is a very important property. Another extremely important property is that we are dealing with low vapor pressure, which means that if we want to use it at 300 degrees, you know what does that mean if you have a steam distribution network? 300 degrees, you're talking about extremely high pressures. This is not the case with molten salts. So regarding pressure constraints, we remove them out of the picture, yet there's something we need to deal with. So there's this shortcut, which is the medium or high boiling point. So these systems need to be prepared to the prevention or to operate with including the event of salt crystallization. Okay, this needs to be foreseen. On the other hand, we also have seen that we have a very good thermal storage capacity, which means that we can have more compact storage systems when we compare that with thermal oil. or even with steam storage, which is a possibility, but not for very high capacities, as we all know. So looking now into molten salt mixtures, the molten salt, there are different types of mixtures. I mean, tomorrow we will have a lecture on molten salt mixtures where you will see these things in detail. So roughly we can see that we have, nitrate-based, chloride-based or fluoride-based mixtures. The mixtures which have been worked, researched, at least in the solar energy fields, are nitrite-based mixtures. And most of all, I mean, and you can see it's called solar salt. We are talking about potassium nitrate, sodium nitrate mixture. This mixture is very well known today. It's state of the art. It's used in commercial plants. It has, it's very good in terms of chemical safety. It's compatible with standard stainless steel alloys, so we will find stainless steel components to deal with all the hydraulics we need. And so this is definitely important if we want to bring these into an industrial, into a commercial use. It has also the potential to be operated at rather high temperatures, so much higher than thermal oils, much higher than steam distribution networks, especially if we don't want to deal with extremely high pressures. So we can operate the systems up to 565 degrees. Yet we know we have this shortcoming. We need to keep it above roughly 240 degrees, which might be a problem, okay? It needs some consideration. Well, but we are now looking into other possibilities. Definitely adding calcium nitrate to this mixture, which then becomes a ternary mixture. It's interesting. Why? Because we can actually lower rather substantially the melting point. So we go from 240 to 130 degrees. This is definitely interesting. And we do not change too much of the other properties. Well, we change something on costs. It's a bit more expensive. It becomes a bit more unstable thermally, so it's more difficult to determine exactly what will be the melting point of this mixture. And there is an aspect which might be important depending on the way we are using the molten salts, which is viscosity. Viscosity, it's about 3 times higher than with solar salts. So if we need to pump a lot these salts around, if we need to circulate the salts, well, we will have a cost there. So these are things we need to take into consideration. Yet, there is the possibility. If you think of using molten salts as a neat storage medium under a phase change material concept, what you can actually see in this table is that we have melting temperatures ranging from 100 to 400 degrees. So this gives us a very wide range of potential applications, which definitely it's an important thing to mention. So challenges and opportunities, well, definitely whenever we address the use of molten salt in any application, but now in industrial applications, might be we will start to have to deal with different constraints regarding the selection of materials, okay? Especially piping, hydraulic components, heat exchangers, and so forth. So this is something which needs to be considered. Potentially, there is an overcost on these materials. On the other hand, we have the questions regarding freezing prevention, okay, which also need to be considered. Yet, definitely, we see a very strong potential for the manufacturing of very compact and very efficient storage systems with the possibility of embedding, of integrating different energy sources, including waste heat. So definitely we see potential there. So this has not yet reached commercial state. Actually, this is a new research topic in the field of using molten salt in energy applications. I mean, for those who are in the solar process heat topic, definitely we see the potential here, both in terms of technical feasibility, but especially in terms of economic competitiveness. Okay, and this pretty much ends my presentation. You have a number of references there. Actually, I must refer that some of these presentations will be made available to you. If not all, some will be made available to you. Thank you so much. I don't know if you have any questions here, or I don't know if the attendants, the remote attendants, have the chance to make questions.
No questions.
No questions. Okay, so maybe I've used already my 15 minutes. Thank you so much.
Thank you, Pedro, for your overview on the application of molten salt on the field of thermal energy provision to industries, and also the application of Carnot batteries that will be deepened tomorrow. Now, according to the agenda, we should have the coffee break.